Hi students. There is a saying that conductivity of ions is constant at infinite dilution and it does not depend on nature of its coion. Okay, let us see how this happens. And today we are going to discuss about Kohlrausch's law. The course outcome for this is develop fundamentals of electrochemistry in engineering processes and the Bloom's taxonomy level is applied. The learning outcome would be at the end of this lecture, you will be able to define what is Kohlrausch's law and also you'll be able to determine equivalent conductance at infinite dilution, especially for a weak electrolyte. In last lecture, we saw that for strong electrolytes, it varies with concentration and we obtain a straight line and this could be extrapolated to cut the y-axis and that value is lambda naught. Whereas for weak electrolyte, even if we extrapolate, it won't cut the y-axis. So it is impossible for us to determine the lambda naught value. See, the straight line, it cuts the y-axis so that we can determine the lambda naught value, whereas for weak electrolyte, it goes parallel to the y-axis. So it is impossible for us to find the lambda naught value for a weak electrolyte graphically. And that could be achieved by what is called Kohlrausch's law. So what Kohlrausch's law states is that um, each ion moves independently of its coion, especially at infinite dilution. Okay, so at infinite dilution, when dissociation of an electrolyte is completed, an intrionic effect also will be vanishing. And ions migrate independently in the solution and contributes a definite and constant value of molar conductance of the electrolyte. That means to say, at infinite dilution, each and every ion will become a shareholder. Say for example, if you have 100 molecules of an electrolyte, you'll have 100 positive ion and 100 minus ion. That means to say it would have undergone 100% dissociation and all the ions will be shareholders for conductance. That is a Kohlrausch's law. And so at infinite dilution, when dissociation is complete, each ion makes a definite contribution towards equivalent conductance, or we can also say as molar conductance, irrespective of the nature of ion with which it is associated. Okay, and the value of equivalent conductance at infinite dilution for any electrolyte is the sum of contribution of its constituent ions. Consider sodium, the set of pairs of sodium chloride and potassium chloride, sodium nitrate, potassium nitrate, sodium bromide, potassium bromide. See, if at all you measure the conductance of these pairs, the difference will remain more or less, the difference will remain the same. That means to say, even if they're associated with any other atom or any other ion, they remain the same. Okay, so Kohlrausch has observed that at infinite dilution, the difference between conductivities of sodium and potassium salts, it is constant irrespective of the associated anions as tabulated below. So he argued that constant difference is found in the conductivities of the above pairs. So this could be ascribed to the fact that the mobility of the sodium and potassium ions at infinite dilution, it is not at all influenced by the nature of its counter ions. So the ions at such low concentration migrate in the electric field as they are independent and they show same ionic conductivity irrespective of the nature of counter ion. So we can calculate the infinite dilution. Okay, lambda infinity could be calculated using this Kohlrausch's law. So lambda infinity of AB minus lambda infinity of CB will be equal to, see, B is common for both, so B will get cancelled and finally you'll arrive at lambda naught of A minus lambda naught of C. Okay. So we can, we have three applications for Kohlrausch's law. The first one is we can determine the equivalent conductance at infinite dilution for any weak electrolyte. Say for example, for acetic acid, acetic acid, the lambda infinity, according to Kohlrausch's law, this could be written as lambda naught of acetate ions plus lambda naught of H plus ions. And if it is sodium acetate, it is lambda naught of acetate plus lambda naught of sodium. And for HCl, all these are strong electrolytes. Sodium acetate, HCl, and NaCl. These three are strong electrolytes. Okay, just like algebraic equations where we can add, subtract to get the value of x and y. Here also we can add the equivalent conductance of strong electrolytes to calculate the equivalent conductance of weak electrolyte. So lambda naught of acetic acid will be the sum of lambda naught of sodium acetate and HCl minus lambda naught of NaCl. See, if we split and write for sodium acetate, it will be acetate plus sodium. HCl, sum of H plus ions and Cl minus ions. NaCl, Na plus and Cl minus ions. Now cancel the common terms. Finally arrive at acetate ion and H plus ions, which is the sum of lambda infinity of acetic acid. Okay, in the same way we can also determine the lambda infinity of a weak base like ammonium hydroxide. Okay, we need to have the values of ammonium chloride, sodium hydroxide, and sodium chloride. Okay, so if you cancel the common terms, you'll arrive at, okay, which are all the common terms we have? Chloride and sodium common terms. The left out is NH4 plus and OH minus, which will give the lambda infinity of ammonium hydroxide. To understand, to have a better understanding, I have given a sum. See, to calculate lambda infinity of acetic acid, we are taking into consideration lambda infinity of HCl, NaCl, and sodium acetate. Okay, so HCl and sodium acetate are added, and NaCl is subtracted, which will give you the value of acetic acid. So this is the first application, and the first application is to calculate the lambda infinity value of a weak electrolyte at infinite dilution. Okay, and the second application is to determine the degree of ionization, that is alpha. Alpha is equal to actual number of ions formed due to the partial dissociation by expected number of particles formed due to the complete dissociation. A complete dissociation is achieved at infinite dilution, whereas actual number of ions formed due to partial dissociation is available at a particular concentration. So what we can do is we can replace these two terms by equivalent conductance at a particular concentration and equivalent conductance at infinite dilution. And according to Kohlrausch's law, lambda naught is sum of lambda naught of plus ion plus lambda naught of minus ion. So this is how we can calculate degree of dissociation for a weak electrolyte. See, for acetic acid, they've individually given H plus and CH3CO minus. If you sum it up, you'll get acetic acid. Okay, acetic acid 390, and at particular concentration the lambda m value is 39.05. So alpha is equal to lambda m by lambda naught. So lambda m is 39.05 and lambda m naught is the 390.5. So the degree of dissociation is 0.1. See, from this you could understand at particular concentration, since this is a weak electrolyte, see the conductance is only 39.05, whereas at infinite dilution it has increased 10 times. Okay, so at infinite dilution the equivalent conductance or molar conductance increases for a weak electrolyte drastically. And the third one is to determine the solubility of the sparingly soluble salt. We know like lambda equivalence is 1000 kappa by C. Okay, for any sparingly soluble salt, the concentration will remain the same. Or in other words, sparingly soluble salt means it will dissolve only to smaller extent, which will remain the same at particular concentration as well as at infinite dilution. So what we can do is we can replace, see, actually kappa is equal to 1000. Okay, lambda equivalence is equal to 1000 kappa by concentration. That concentration could be replaced by solubility. Okay, so we want to determine solubility. So solubility will be equal to kappa into 1000 by lambda. See, two modifications we are doing. Concentration is replaced by S, as well as lambda equivalence is replaced by lambda naught, because this is a sparingly soluble salt. But this cannot be done for a completely soluble salt. Okay, we are taking the lambda equivalence representation. Lambda equivalence is equal to 1000 kappa by C, where C is replaced by S and lambda equivalence is replaced by lambda naught. And according to Kohlrausch's law, lambda naught is equal to lambda naught of plus ion and lambda naught of minus ion. So we can replace lambda naught is lambda naught of plus ion and lambda naught of minus ion. So this is how we can calculate the solubility of the sparingly soluble salt. So to sum up, these are the three applications of Kohlrausch's law. One is to determine the lambda naught of weak electrolyte. Second one is to determine degree of dissociation of a weak electrolyte. And the third application is solubility of a sparingly soluble salt. So I think you were able to understand what is Kohlrausch's law, and you were also able to determine the equivalent conductance, solubility product, and degree of dissociation. Thank you.